In this lecture, we'll discuss a few algorithms to obtain a minimum spanning tree from a graph. There are two different algorithms that we'll discuss. In the first video, we'll discuss the Kruskal algorithm, and then in the second video, we'll discuss the Prim's algorithm. So let's discuss the Kruskal's algorithm to find a minimum spanning tree. So the idea of the Kruskal's algorithm is very simple. It starts from a forest of trees. So if there are n vertices, it says that I have n different trees in the graph, which means that we say that there is no edge in the graph, there are only vertices. So we'll start from that point. And then what we do is that we'll pick one edge to connect any two other vertices. So on what basis we pick the edge is that we'll sort the edges on the basis of their weight or on the basis of their cost, and the sorting would be in the ascending order, which means that the edge that has the smallest weight should be the first one to be picked. So the logic is very simple. Pick the edge that has the lowest cost and then use it to connect two vertices of a graph. So it means that what we have done so far is that we have actually uh, used, or we have actually picked the best available option to connect any of the two vertices in the graph. So if I repeat this process n minus 1 number of time, if I have n vertices, then I need to pick n minus 1 edges that are of the lowest cost, and they connect two disjoint portions of the graph. So that's the entire logic. And the proof is that if I pick the edge of the lowest cost in every step, then the resultant or the sum of all the edges would be the least. So that would be the minimum value, because I'm not using any edge that is of a bigger cost before trying an edge that is of a smaller cost to connect the graph. So on this logic, what we will do is that um, while I pick a edge, I would only check one condition, that it does not create a cycle, or it is not the redundant edge. It does not connect the two already connected parts of a graph. So that's the only condition that I need to check. So um, uh, formally, the halting condition or the stopping condition of the algorithm is that until I have picked v minus 1 edges, that is, I now have a complete minimum spanning tree. Or the second condition is that the graph is not connected. In that case, what I would do is what I would have is that I have tried all the edges, still the graph is not connected. Okay, so in that case, I would just stop the algorithm, and I would say that I have found a spanning tree that connects a portion of the graph, but it's not the spanning tree that actually connects the entire graph. Okay, so in that case, I would have a spanning tree, but that would not be a spanning tree of the entire graph. Okay, so that would only be a spanning tree of the connected portion of the graph. So this is the overall algorithm. We'll see this algorithm with the help of an example. I pick the cheapest edge. I check if it creates a cycle. If it creates the cycle, I reject it. Otherwise, I add it to the forest. Okay, so that's the entire logic. That's the logic, and we'll see how we can use this to find a minimum spanning tree. So in this example, I have this graph, and for this graph, what I specifically do is that um, at the first step, what I need to do is that I need to uh, actually consider this graph as these disconnected vertices. So in this after the first step, what I have is that I have only these vertices, and I ignore all these edges in this graph, and I pick the edges, sort them. So I sort the edges, and now this is the edge with the minimum cost. This is the second edge with the minimum cost. So these are the sorted sequence of the edges. Okay, and what I actually um, considering what I'm actually considering here is that there is no edge in the graph. There are only these n number of vertices, and I need to pick n minus one edges out of these number of edges. So there are, I guess, 16 edges. I need to pick only 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I need to pick 9. There are n is equal to 10 vertices, so I need to pick 9 edges out of these 16 edges. So what I would do is that I would start by picking the edge with the minimum cost. So this is the edge AD. So I pick the edge AD. A and D were not connected before using this edge, so I added that to the minimum spanning tree. Then I move on to the next edge, that is CF. So C and F are not connected so far, so I use that edge as well. Then this is C and E. So C and E are not connected, so I pick this edge and use it in the spanning tree, in the minimum spanning tree. Then I have this edge E and G. E and G are not connected, so I just use it to connect these two vertices. So if you see that, uh, if I try to use this edge between F and G, that would be a cycle. You see, these four vertices were already connected via three edges. It means that this edge, if it comes into play, I need to reject it. Okay, so let's see if this scenario comes up. So the next edge in the sorted sequence is between H and J. So this H and J, these are not connected. So I connect them via this edge. And you see now I have 1, 2, and 3 portions or three subgraphs that are now connected, and all this edge, this vertex B and this vertex I are two different trees. So I have in fact 5 trees. These 3 trees are blue, and these 2 single node trees are already there. So I have 5 trees now, and these 1, 2, and 3 trees, if I need to connect them with these two portions, I need just a few more um, edges. Okay, so let's see. So far I have picked 5 different edges. I need only 4 more. Okay, so picking this edge between F and G, then now this edge is creating a redundancy because it is between the already connected portion of the tree. Both the vertices that this edge connects are already in the connected part uh, of the of the graph. So I would not pick this edge. I ignore this edge. I move on to the next edge, that is between G and I. So G and I are not connected. I use this edge. Next is I and G, I and J, and this is also connecting to disjoint sets. Then I this is the edge AB. This is also between the two disjoint parts. B and D. No, this is actually creating another redundancy. So I ignore this edge, and this B and C edge is the final ninth edge that I need to pick. So you see, all the vertices are now connected, and I do not need any more edge. So I can just stop this algorithm here. I do not need to check any of the 5 remaining edges, because if you just go to the proof that I already discussed, is that if I use this edge, that is of a higher cost. And if I just try to prove that removing an edge from this graph and using this edge G and J would be of a minimum, would create a minimum spanning tree, then see, all the edges that I have already picked are of the cost less or equal than this 4. So removing an edge and adding this edge would not reduce the cost of the spanning tree that I have so far. That can be equal to this um, to this already existing cost, but cannot be lesser than that, because all the edges that I have picked so far are of the equal or the less cost. Okay, so using this logic, I can ignore all the edges of the higher cost. So that's the final solution. And you see, that was the initial graph, and I picked 9 edges to make this a tree. So if I just use this C as a root, then this is a tree, and I have only a unique path from C to any other node. So in this way, I have picked up a minimum spanning tree from the graph. So that's it for the Kruskal's algorithm. Um, or Now we'll discuss a few more details of this algorithm. That um, there was a step of detecting a cycle in the graph. So how can we do that? So for example, that's another graph. From this graph, if I just try to find the minimum spanning tree using the Kruskal algorithm, I would actually start with the edges sorted in the ascending order of the cost, and then if I just run this algorithm, I would find this minimum spanning tree. Okay, so this is the minimum spanning tree, but how can I actually um, detect a cycle in the graph? If I pick an edge, for example, if I now pick the edge, this maybe this edge between D and F, that is of course 14, this creates a cycle. How can I actually detect that cycle? So that's very simple. Simply need to perform a traversal, maybe a breadth first or a depth first traversal, starting from any one node from this tree. So if there is a cycle, what I would have is that any of the nodes would be repeated in that reversal. Okay, we saw in the previous lecture that in a breadth first or a depth first reversal, there are times that we need to detect if a node is already visited or not. And if a graph is visited, we know that a cycle is there. So we just need to perform a traversal to detect a cycle. That is of order v times. Because in the spanning tree, I do not have redundant edges. In the connected graph, I have only the required number of edges. So if there are 6 connected vertices in the subgraph, then there would be only 5 edges. Okay, so detecting a cycle between 6 vertices is only of the cost of uh, 5 or maybe 6 steps, and I would reach back to this specific node. So that's how we detect a cycle. And then the second thing that is actually a hidden cost is that how can we detect that the edge that we are picking is between two different parts or disjoint parts of the graph. So that's very simple. You actually use the data structure set. So what we have initially is that all the vertices are in different sets. So if there are n vertices, we would have n different sets. And upon adding one edge, what I would only do is that I would check the presence of source and the destination of the edge in the sets. So if both these vertices are in the same set, which means that they are already connected, and if the source is in one set and the destination is in the other set, it means that these two sets, uh, each set is representing a connected part of the graph. And for if the two destinations of the edge are in two different sets, it means that these two vertices are not connected to each other, and I would use that specific edge to connect the two sets. So once I use the edge, what I only need to do is that I need to take the union of these two sets to make one single set. So I will keep combining the sets to make a bigger set, and eventually I would have all the vertices in only one set, and that's the termination condition of the Kruskal's algorithm. Okay, so that's it for the details of the Kruskal's algorithm. In the next video, we'll discuss the Prim's algorithm.